All right, Algebra 2, welcome back. We are going to continue on with learning the unit circle. Last time we were together, we took a look at these common spots on the unit circle, places based on the angle of rotation that are just our go-to values. To know the sine and cosine of 30 degrees, 45 degrees, 60 degrees, and all of those rotations of those angles. They're all based on 30, 60, 90 triangles or 45, 45, 90 triangles. And so we have the multiples of 30 degrees walking their way around the unit circle, and we have the multiples of 45 degrees. Those are our common pieces. And last time we looked at those special right triangles, those 30, 60, 90 triangles with the radius. Remember, the radius of that unit circle is 1. And so then that made this shorter leg 1/2. That was the y coordinate. And that made the longer leg √3/2. So here at 30 degrees, we are at the ordered pair √3/2, 1/2. And we found out that that x-coordinate represents that cosine because it's the adjacent side over the hypotenuse of 1. So cosine's x. And then that y-coordinate is that opposite side over a hypotenuse of 1. So sine is y. And we can use all of those ordered pairs walking around the unit circle to find the sine, cosine, and cosine at each of those common angle measures. And then we also knew or discovered that tangent would be the opposite over adjacent. That would be the y-coordinate over the x-coordinate, or sine over cosine. So tangent was the sine over the cosine. And we're almost there with the whole unit circle. We just have one more set of numbers to complete in here. If you notice, there's another set of blanks walking around this unit circle. By the way, if you haven't grabbed your old unit circle from the last lesson, do that, because we're going to be filling in that last set of blanks. There is another way to describe the position around the unit circle, not based on the angle of rotation, but based off of the length here of this intercepted arc. You can see at 30 degrees, it stops right there, and there is a length to this arc. And so it is an arc measure. That is what we call a radian, okay, and radian measure. And so we have a definition of radian measure that I would like for you to take a look at. A radian is the measure of a central angle. So we're still talking about referring to a central angle, but it's no longer the angle of rotation in degrees. It is the intercepted arc. And a radian is equal to the radius of the circle. So a radian is a unit of measure, like feet is a unit of measure and centimeters is a unit of measure. Radian is the unit of measure, and it's based off of the radius of the circle. So in the unit circle, we know the radius is 1. If the radius of the circle were 5 would be the length of, like 5 centimeters. That would be the length of 1 radian. So this is a little bit new of an idea. It's sort of like learning a foreign language where you translate from English to, say, Spanish, and you have 2 words, one in each language, that refers to the same thing. A degree measure and a radian measure refer to the same thing, a measure of a central angle, but they're in 2 different units, 2 different languages. So let's see what we can do in terms of discovering what those radian measures are on our unit circle. If you got a chance to print out this piece, these blank unit circles, they are not a complete unit circle. Notice here on this one, I've just pulled off the 30, 60, 90 degree markings on that unit circle. And you can tell because there are just 3 pieces there in that quadrant. And we know a quadrant's 90 degrees. So this would be 30 degrees, 60 degrees, 90 degrees. And it is all of those multiples of 30 degrees. So if we think about looking at an arc length, like that actual length, if we were walking along there, that's part of the entire circumference of a circle. So we need to go back to some geometry things and remember that circumference is equal to 2 times pi times the radius. And some of you are saying, well, I thought the circumference was pi times diameter. Well, that's true as well. But since we're dealing in radians, we want to actually use the form that deals with the radius because 1 radian is equal to the length of the radius of our circle. And in the unit circle, do you remember what the radius is? It's 1. R is 1 in our unit circle. So the circumference, the distance all around that circle is 2 pi. That is key to us understanding what the radian measure at each of these pieces is going to be. Because if we start here and we don't go anywhere, it's at this point right here, then we've gone 0 radians. But if we picture a bug walking around this entire circle, all the way around, we've gone 1 circumference. That is 2 pi radians, because the circumference was 2 pi of the radius, which was 1. So 2 pi radians is all the way around. Now we're just going to think in terms of fractions. Well, if all the way around the unit circle was 2 pi, half of that distance through quadrant 1 and quadrant 2 would be half of 2 pi, which would just be pi. So equivalent to 180 degrees is pi radians. Now, we can just cover up this bottom piece and we can think of this semicircle, the top part of the unit circle, as being pi radians. Now notice at my 30, 60, 90, 120, 150, 180 markings, that has broken this half circle into 1, 2, 3, 4, 5, 6 equal parts. So all 6 of them are pi. So this distance right here must be 1/6 of pi. So we call that pi over 6. Now we're just going to count by pi over 6s because each of these pieces is the same size. So this is 1 pi over 6. This is 2 pi over 6. This is 3 pi over 6. This is 4 pi over 6. This is 5 pi over 6. And I'm going to go for the whole circle here. Keep counting 5 pi over 6. This is 6 pi over 6. Well, isn't 6 over 6 1? So that's why it's pi. So 6 pi over 6, keep counting. 7 pi over 6. 8 pi over 6. 9 pi over 6. 10 pi over 6, 11 pi over 6, and 12 pi over 6. Well, 12 divided by 6 is 2, so we're back to 2 pi. And those are most of our radian measures, all of those at the 30, 60, 90 degree markings. Now, some of these can be and should be reduced. Notice this can reduce to pi over 3. 4 pi over 6 can reduce to 2 pi over 3, and I accidentally skipped this one. 3 pi over 6 can reduce to pi over 2, 1/2 pi. 5 pi over 6 doesn't reduce. This was 6 pi over 6 reduced to 1 pi. 7 pi over 6 doesn't reduce, but 8 pi over 6 reduces to 4 pi over 3. 9 pi over 6 reduces to 3 pi over 2. 10 pi over 6 becomes 5 pi over 3. 11 pi over 6 doesn't reduce, and this was 12 pi over 6, which we knew was 2 pi. And so these pieces, these reduced radian measures, are the ones we want to use. Now, when I go and create the unit circle, though, I always think in terms of just counting by those pi over 6s, and then I reduce. Now notice each quadrant is pi over 2, so we could count just by quadrants. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. I could keep going. 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2. If I had angle measures in radians that were more than 2 pi, you just keep counting. Notice every 2 of these is pi over 3 radians. So I could count every 2. There's 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3. And so there are lots of different ways to count. But what about those angles on the unit circle that we're missing? All of those 45-degree angle markings. Well, take a look at the unit circle below. I've pulled off the 45 markings. Let's just put, we know this is 0 radians, and it's also coterminal with 2 pi radians, and we still know that halfway around the circle will be pi radians. But now look at this 1 pi. Instead of being divided into thirds, instead of being divided into sixths, like the one before, it's divided into 1, 2, 3 fourths. So now we'll count by fourths. Here's 1 pi over 4. Here's 2 pi over 4, but that reduces to pi over 2, which is the same marking on the other one, which is a good thing. So 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, which reduces to 1 pi, 5 pi over 4, 6 pi over 4, which reduces to 3 pi over 2. That was 6 pi over 4. This is 7 pi over 4, and 8 pi over 4, which reduces to 2 pi. Now we have all of our radian markings. So let's go ahead and grab our unit circle and fill those in. When I am filling in a unit circle, and if we were in class together, I'd be having you do this like for a quiz, just fill in a blank unit circle. I think about those same things. I count in terms of sixths and fourths. So I start with 0, and I usually put my pi over here just to remind myself, and my 2 pi before I start counting in those fractions. I'm just going to bounce through all of the 30-degree angle markings, counting by sixths. 1 pi over 6, 2 pi over 6, which reduces to pi over 3. 2 pi over 6, 3 pi over 6, which reduces to pi over 2. 4 pi over 6, which reduces to 2 pi over 3. 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, which reduces to 4 pi over 3. 9 pi over 6, which reduces to 3 pi over 2. 10 pi over 6, reduces to 5 pi over 3. 11 pi over 6, and back to 12 pi over 6, which is 2 pi. There are my 30-degree markings in terms of radians. Now I'll go back at those 45-degree angles and count by fourths of pi. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. And now our unit circle is complete. It has all of the angles in terms of degrees, radians, and the corresponding ordered pairs. And those ordered pairs are important because it tells us what the sine and cosine of those angles are. And we will do the same evaluating in radian measure, in radian mode, if you're using your calculator. But we don't need to because we have the unit circle. But we will use those same ideas that cosine's x and sine is y. And so we can actually find different values here. Let's use our unit circle. I don't know if you can see that. We're going to look for these three values: the sine of 5 pi over 6, the cosine of negative 3 pi over 2, and the tangent of 4 pi over 3. So let's find the sine of 5 pi over 6 first. Go to your unit circle. Take your finger and put your finger on the spot of 5 pi over 6. Well, that's going to be right there. And so we are looking for the sine of 5 pi over 6. Sine is y, so look for the y coordinate. It's 1/2. So the sine of 5 pi over 6 equals 1/2. All right, the next one was the cosine of negative 3 pi over 2. When you're dealing with negative angles, whether in degrees or radians, you're going to start here at standard form, but instead of going counterclockwise, you're going to go clockwise. Now it said negative 3 pi over 2. Don't just go to 3 pi over 2, because that is not the same as negative 3 pi over 2. And don't just make those negative, because that won't work. You have to think, well, to get to 3 pi over 2, I had to go 1, 2, 3 quadrants in the positive direction. So to get to negative 3 pi over 2, I need to start here and go backwards those 3 quadrants. Here's negative 1 pi over 2, 2 pi over 2. Here is negative 3 pi over 2. It is coterminal with pi over 2. So this is where negative 3 pi over 2 terminates. And I'm looking for the cosine of negative 3 pi over 2. Well, the cosine is that x-coordinate. So that would be 0. Okay? Cosine of negative 3 pi over 2 would be 0. The last one is the tangent of 4 pi over 3. Well, that's a positive angle, so look for 4 pi over 3 on your unit circle. That is right down here in quadrant 3. And the tangent is the sine over the cosine. So if I'm trying to find, I'm just going to write this here, the tangent of 4 pi over 3, that's going to be the sine, which is the y coordinate, over the x coordinate, negative 1/2. You do not want to leave your answer like this. This is called a compound fraction. Fractions within a fraction. You don't want to do that. The nice thing is that they both have a denominator of 2. So if I multiplied both top and bottom by 2, those 2's would cancel out. And so the tangent is negative root 3 over negative 1. Well, the negatives also cancel out. It is equal to just root 3. So the tangent of 4 pi over 3 is root 3. So in essence, we're doing the exact same thing we were doing with degree measure, finding the sine, cosine, tangent on the unit circle, those nice spots on the unit circle, but we're talking in terms of radian measure, a different way to describe those same angles. All right, email me any questions. Talk to you later.